Good morning, everyone. So my name is Antonio Acin, and I work at ICFO in Barcelona, and I'm chairing this session on basic science, quantum communication, and quantum computing. And our first speaker this morning is Professor Eugene Polzik from the Niels Bohr Institute in Copenhagen. So please, Eugene.
Thank you very much. It's a pleasure to be the first speaker, and I would like to see my presentation now. Thank you. So it's about fundamental science, and I will really speak about physics. So the subject will be sensing of fields and forces, and I will address the issue of standard quantum limits, which is, of course, paramount for sensing applications. And by the end of the talk, you should leave with the sense that there is no limits to quantum sensing. So being from the Niels Bohr Institute, let's go back in time and discuss where does this quantum limit of the measurement of position, for example, and trajectories, where does it come from? So we have a wizard, and the wizard looks at a particle, a photon is scattered off the particle, and you see the photon, but the particle, of course, got a kick. Although it's a kick, but it's not a billiard ball, right? Because the particle is also has wave properties, and the better you see where the particle was, the worse is the uncertainty of the momentum that this particle has obtained from this interaction with the photon. And so if one puts together a simple quantum mechanical calculation using the uncertainty principle, you very quickly find that actually there is a limit, which is called the standard quantum limit, with which you can trace the particle's motion. And this depends on the mass and then the time of the observation. So there is a limit. At least there was a limit. And the talk will be addressing this question. Are there really quantum limits for measurement of forces in motion? And the way it is sometimes referred to is trajectories without quantum uncertainties. And I add here in the negative mass reference frame, because this will be the basic physics behind this approach. And sometimes it's also called quantum mechanics free subspaces. And you can see the key references on the screen. So this is a classical trajectory. This is what we usually think of a quantum trajectory. And what we need to achieve, or we want to achieve, is that the quantum trajectory of a particle can be traced without any limits. So let's take a look at a mechanical oscillator. So here is an oscillator, and a typical situation, at least in the lab or in your sensor, it's a small oscillator, but you know, it's a finite size thing. So it has its 0-point fluctuations, which relate to the basic quantum uncertainty of about a femtometer, but it's easy to measure a femtometer displacement in the lab. People who work with optics know about it. So, and again, basic quantum mechanics, the variance of the position and the momentum is bound from below because those are non-commuting operators. So what it actually means, as we saw in the previous example, is that you measure X and you impose the back action on P, quantum back action of the measurement. And in case of an oscillator, those X and P will be like the dimensionless amplitudes in front of sine and cosine of the motion. So you can think of it in the following way. At some point in time, you're measuring X and you're putting back action in P, of course. So quarter period later, you're measuring P, putting the back action on X. And the more you measure, the more back action you put on it. And so looks like a dead end. And yet I will show you if you choose the right reference frame for this measurement, then you can measure both position and momentum with arbitrary accuracy as follows. So the three steps you need to take is any trajectory is defined relative to a reference frame, of course. And let's quantize this reference frame. Let's make a measurement of motion with regards to another quantum object, which serves as our reference frame. And then this reference system should have an effective negative mass. And I will show you a simple physical example of implementation of this effective negative mass. And finally, an entangled state of the reference system and the probe system should be generated, and off we go. So just to remind you about one type of entanglement I will be looking into in this talk, it's the Einstein-Podolsky-Rosen entanglement. The difference of the positions and the sum of the momenta of the two particles are commuting operators, so they can be measured with arbitrary accuracy. And this was the discussion from back 1935. And somewhat later, also already 20 years ago, the condition on the entanglement between the two particles has been shaped. You need to know the difference of the positions and the sum of the momenta better than a certain boundary which comes from the commutation relation, and then the particles are entangled. So let's assume, like I said, that we want to measure a relative motion of our particle described by x and p and the reference frame, reference particle, which I described by x naught and p naught. And I'm allowed to have the difference of x's and the sum of p's to be defined with arbitrary accuracy. So now I write down a position of my particle as a function of time in the reference frame of another particle, x naught. So of course, kinematics, it's the difference of the two positions at the time zero plus the difference of the momenta of the particles times t. And now when I put, instead of the difference of the derivative of x, I put the difference of p's, then you see that it's a problem, because we have the difference of x's and the difference of p's, they don't compute, and the trajectory diverges. However, if I simply take a formal requirement that my reference system has a negative mass, then of course I have the change in the sign, and then the trajectory is defined as a difference of x's, the sum of p's, commuting variables. We can measure them and trace the trajectory well. So this is how the negative mass comes about. And if I manage to find a system like that as my reference, I should be able to make measurements and sensing of whatever position, forces, whatnot, with arbitrary accuracy. The same thing is true for an oscillator. So if I now take an oscillator, then instead of a negative mass, I will have a negative frequency principle. And again, if the frequency of my reference oscillator is negative, then I have this change in the sign, and my trajectory, or the difference between the positions of the two oscillators, is defined by commuting variables. And one can show that if the two systems are entangled, then it's a sufficient condition for tracing those two motions, relative motions, with arbitrary accuracy. And now let me introduce the negative mass oscillator. It's actually the thing that many of us work in the lab with. And let's say it's a collection of spins. I have many of them. I orient them all in the up direction, z direction. But then, of course, we know that there will be an uncertainty of this position, which will be defined by the vacuum fluctuations. Fine. And then let me try to make an excited state of this system. But first, make it an oscillator by putting it in the magnetic field. So now the spin is oscillating, it's an oscillator. And what would be the first excited state of this oscillator? Well, it will be the situation where it's a superposition of one of the end spins being flipped. And this state will have a larger dimension on this sphere. And since it's larger, then it's by definition closer to the South Pole. It's a larger state, it's closer to the South Pole. And of course, it has lower energy. So I have excited my oscillator and I reduced its energy. So I call it a negative mass or a negative frequency oscillator. And making something like that in the lab is possible, of course. You take an ensemble of atoms, you arrange them in one direction, and then you start playing with it, and you get the negative frequency states and negative mass oscillators. So this can be used for sensing magnetic fields, and it's been used. So my atomic ensemble is a large thermal ensemble of atoms in a very special spin-protected environment. Atoms are in the magnetic field. They can move around, but they keep their spin coherence. And so let me just show you how this back action that we want to suppress in the end works. So imagine I have linearly polarized light, and I send it through the atomic spin, which is precessing in the magnetic field. Of course, if I measure at a given point and my spin is looking in some direction, then I put the back action in the orthogonal axis, as I've shown you in one of the first slides. And so again, the more I measure, the more back action I get. And in the experiment, if we look at the spectrum of noise of this oscillator, and what you see here is actually the noise measured optically, and it's completely dominated by the quantum back action of light on this oscillator. And this oscillator can be the negative mass oscillator or positive mass oscillator. And I show you the example of a relatively old experiment where we used the positive mass oscillator, which is oriented with a spin down, and the negative mass oscillator with a spin up. And we have demonstrated that by sending light through both systems like that, we can entangle them, measure and entangle. And the simple geometrical interpretation of this entanglement is that two spins which are entangled are more parallel than the Heisenberg uncertainty principle allows you to measure on each of them separately. And of course, if you have two exactly anti-parallel spins, then you can subject one of them to a perturbation, and you can measure this perturbation as good as you wish in principle, of course. So we used those principles to make a measurement of the tidy magnetic field, and we demonstrated entanglement with this experiment by sending light through those two ensembles and making a measurement of the magnetic field. And lately we've been using it to measure the magnetic fields of small biomedical objects. So we achieved some pretty impressive sensitivity, which is in the sub-femtotesla range. So the second half is about sensing motion using the same principle. And roughly speaking, you use a mechanical oscillator to sense motion, and you use this atomic inverted oscillator as a negative mass reference frame. And so this is our wonderful mechanical oscillator. It's a silicon nitride membrane. It's macroscopic, you know, it's like a fraction of a millimeter in size, very thin though. And we are going to try to measure the motion of this membrane beyond the Stern quantum limit. The membrane is positioned in a cryostat, 8 Kelvin, nothing very spectacular. And we send light through the optical cavity where the membrane is, and you see the membrane is oscillating, and we're measuring this oscillation. And what you see in the upper left corner is the quantum backaction dominated measurement of this membrane oscillation. So we first cool the membrane to the ground state of motion, and we start looking at it. And the more we look, the more we disturb it by the quantum backaction. And you see this measurement completely dominated by the quantum backaction. Okay, so now we have two systems, the mechanical oscillator and the magnetic spin oscillator with an effective negative mass. And we want to demonstrate first that we can entangle them, and second, that we can use this entanglement for measurement beyond the Stern quantum limits. So that's the layout of the experiment. On the left-hand side, you have the spin oscillator. On the right-hand side, the mechanical oscillator. This is our already familiar spin quantum oscillator. And this is our mechanical oscillator. So we send light through. And the first thing we want to show is that we can cancel out the quantum backaction of the measurement. And here you see on the left-hand side, the quantum backaction dominated spectrum of the membrane. On the right-hand side, quantum backaction dominated spectrum of atoms. Notice that it's a logarithmic scale. So indeed, it's seriously quantum backaction dominated. And now we tune the atomic frequency in resonance to the mechanical frequency. We combine those two measurements, and what we get is a seriously reduced quantum backaction, which is now this checkered area. And it's a 6 dB reduction, a factor of 4 reduction of quantum backaction of the measurement. So with this at hand, we can proceed to demonstrate that we indeed can entangle our mechanical oscillator with a negative mass reference oscillator. And those are the heroes in the lab. And the generation of entanglement, as I mentioned before, simply means that we can make a measurement, and with this measurement, we can measure the motion of the mechanical oscillator with respect to the magnetic oscillator with sensitivity exceeding the Stern quantum limit. And we can do that because one of the oscillators has an effective negative frequency. So without going into details, this is the result of the experiment. And this is the result indeed, where the variance of the difference of the positions and the sum of the momenta is measured beyond the quantum limit set by the usual single oscillator measurement. So here I would like to show you the experimental result. And what you observe here is the trajectory in the phase space of the two oscillators. And one of those lines is the prediction, and the other is the measurement. And you can see that the prediction and the measurement are correlated better than the blue circle, which describes the Stern quantum limit. So indeed, it is possible to trace the trajectory of an oscillator in phase space better than the Stern quantum limit if you make it in a correct reference frame. So, final few minutes, how this can be actually used for something truly exciting, and that is for observation of gravitational waves. So gravitational waves have been observed, and they've been observed using a huge interferometer. And that's the interferometer where the two of the end mirrors are suspended in such a way that when the gravitational wave comes, it rocks it out of phase. And so you unbalance the interferometer and you observe the gravitational wave. And it's been 25 years of hard labor, and finally they did it. But what is the limit? The limit of the sensitivity of this measurement is actually quantum mechanical. And what you see here is the spectrum of noise of the large interferometer for gravitational wave observation, LIGO. And it is shown in the frequency domain, which is relevant for gravitational waves, that is from tens of hertz up to a kilohertz. And in the right-hand side, it is dominated by the shot noise of your probe light, phase noise. And on the left-hand side, in the lower frequencies, where you measure longer, it is dominated by the radiation pressure of light on the mirrors, which is the amplitude noise. And normally you would say, okay, that's as good as it gets, as I've shown you in the first slides of the talk. You cannot do better. You can either improve the phase noise or the amplitude noise. You cannot do both. And yet it turns out that you can do it, at least with the use of this negative mass approach. And the way you do it is you insert into the interferometer your negative mass atomic oscillator and make a joint measurement on both systems. And well, it's a little more complicated than just this ensemble of atoms, but the principle is exactly like I told you in the second half of the talk. You make a joint measurement on the reference frame negative mass oscillator and the system of interest, which is the gravitational wave detector. And in very simple terms, the susceptibilities of those two systems are just opposite, and therefore the back action is canceled and you can make your measurement. So this is the theoretical prediction so far, and the dashed line is the Stern quantum limit, and the solid line is what we expect to observe if we manage to demonstrate the principle with reasonably realistic limitations on the losses and possible imperfections. So we're building up a system which will be used to demonstrate the proof of principle, first outside of the LIGO interferometer, just in the lab. The system involves entangled modes of light and the atomic spin ensemble. And this is the experimental setup on the table. And this is the heart of it, which is the atomic cell in magnetic field. And this is our first result, where we demonstrate entanglement between the light modes that we will be using to entangle atomic system and the prototype of the interferometer. We have pretty good entangled state between the two colors of light. So this gives us some hope. And finally, that's the summary. What I tried to show you is that macroscopic mechanical and atomic objects can be entangled and used for precision measurements of motion, force, and even gravity, with no fundamental limits in sight on sensitivity. Those things can also be used for quantum communication. I didn't have time to talk about it. And thank you very much for your attention.
Okay, thank you very much, Eugene, for your talk and being on time. So we got a question from Johannes Heinzo. I hope I let's read your name as I should. So he's asking about your spectrum plots. I think it was, and the question is, what is on the y-axis? How does the area under the curve relate to quantum back action?
So thank you for the question. The area under the curve is predominantly proportional to the quantum back action. So I don't know if I should go back to the slide. Should I?
If you can.
Well, I need help because I cannot go back to my slides myself. No.
Okay.
Oh, yes, thank you very much. So if we keep going back. Yeah, that one. So the checkered area is precisely the quantum back action, and then the other areas which are smaller are the thermal noise of atoms and ground state noise of the mechanical system. And again, this is a logarithmic scale, so you can see that the joint system has significantly reduced by 6 dB reduced joint quantum back action. Ideally, no losses and very good coupling. You shouldn't see this quantum back action at all, in which case the measurement will be in principle with arbitrary accuracy.
Okay, there is a second question by Stephen Vinskevich. And he's asking, is it true that purity and robustness against noise of entanglement of states that you are using to entangle two different systems of interest affect the total variance of observables?
Are what?
So he's wondering whether purity and robustness against noise of entanglement of those states you are using
are the property of both systems?
If they affect the total variance of observables, the entanglement.
Okay, so if I get the question right, it's an entangled state. So if it's ideal, pure entangled state, then it's of course a pure state. The two systems taken separately, as usual, are in completely mixed state. And the degree of entanglement is directly related to the degree of the purity of the states.
So maybe I have a question also. So what do you have to use to use your system in the LIGO? Can you go back to the slide? What do you have to use? You have to put your ensemble of atoms in one of the arms of the interferometer. How was it?
Okay, let me go further down. Here. So our atoms respond to 852 nanometers of light, and this is non-negotiable. And LIGO works at 1.06 microns of light, and this is also non-negotiable. So we cannot, as in our laboratory experiment, use one and the same beam of light to send through the two systems and entangle them. Instead, we need to start with entangled beams of light, and one of them goes to the atoms, the other one goes to the LIGO, and then a joint measurement is done. And what we're putting together in the lab is the source of entangled light, the central part, and the spin ensemble, the left-hand side part. We're not building our little gravitational wave detector. Instead, we will be simulating the response of the detector with electronics, which is relatively simple. And if we can accomplish that, then we hope to, in the next step, to use it in one of the prototypes for gravitational wave detection.
Okay, thank you very much, very clear. Well, I think we are done. Thank you very much, Eugene, for your talk and your time. And
Thank you.
we should move on to the next speaker. So, Eleni. Okay, yes, we have here Eleni ready for her talk. So yes, our speaker today is Eleni from CNRS in France, who will tell us about quantum communication. Remember, I forgot, write your questions in the live Q&A part in the virtual conference platform. So Eleni, you can start, please go ahead.
Hello. Thank you very much, Tony, for the introduction. Thank you, everyone. It's a pleasure to be at this conference today. So I'm Eleni Diamanti. I'm a research director of CNRS at the Sorbonne University in Paris. I'll be talking to you today. I'll giving an overview of the European efforts that are currently in place, leading towards a European quantum communication infrastructure. So I will go through a little bit the basics of the field of quantum communication and where we're heading, how presently and in particular the European flagship projects contribute to this roadmap in quantum communications in the next few years, and what I believe are the key challenges that we're going to have to address with our work in the next few years to make this happen. So let me start. I find it very instructive to start with maybe I'm not sure the clicker is working. Could you please go to the next slide? Thank you. I find it instructive to start with a small, very small overview of what communication networks are and how we came to have the internet today. So as a reminder, data communication networks and information networks that we're using today are exactly used to share information between computers and other devices. They are telecommunication networks that are meant to exchange data, and they were developed after a very, very long history that lasts for decades. Now it started in the 1960s. As you know, it was dominated by the ARPANET network in the US, and it led to what we call internet today. And it's a ubiquitous tool that we're using our communication networks for everything that we do today. And some of these applications, we didn't even know that they were going to exist at the time of the first stages of these classical communication networks. And you will see this is a bit the point where we are for quantum communication networks today as well. Next slide, please. Important, still on the classical communication network sense, important attributes are the protocols and functionalities. What I'm showing you here is the OC. For the engineers among you, you will recognize it. This is the OC layered description of the communication networks, where you see that we start with the physical layers where the bit information and coding is happening, and then we are going up to several layers that they increase in complexity. They include in particular the transport and routing protocols, and go up all to the application layer. Important characteristics of all these networks is, of course, the range and the topology. You will see in particular for the range that we can start from a few meters, which is a building or a small campus range, go up to metropolitan networks with a city in a city level, and then up to wide area networks where we're talking about whole countries and the planet, which is essentially the level of a planetary connection of the present internet. So how do quantum technologies fit into this structuring of communication networks? Next slide, please. So what has fundamentally changed when you introduced quantum resources in such a network is, of course, that we are working here on the lower layer, on the physical layer of this network structuring, and by encoding information now not to classical bits but to qubits, we are changing in a very fundamental way the way that this information is treated. And this has consequences with the superposition and the entanglement, which are the main fundamental principles of quantum mechanics. It has consequences not only on the physical layer, but of course on all the upper layers of the network structuring, and in particular in the routing of the information, which now needs to rely in particular for entanglement. It has to go through protocols like teleportation and entanglement distribution, and of course up to the application layer, where we see that introducing these quantum resources also has an immediate effect in what applications we can access with our networks. So next slide. So let's go and define again, based on the structure, the quantum communication networks. So these are networks that will link, that are there to link quantum devices, such that we are able to exchange data. After all, this is the traditional definition of quantum communication, is the art of transferring quantum information between distant nodes. Remember, this is how it was first introduced in the field, but also it is important to understand, as I just said, that we can not only enhance and reinforce some classical services that are already present in the classical networks, but we can also introduce new ones. We can use these quantum resources to show a quantum advantage that can come in security, as you are going to see in a second, in a huge massive application area of quantum communication, cybersecurity and cryptography, but also in efficiency, how well and how efficiently we use our network resources, and of course in computation, in the more advanced instantaneations of the quantum networks. So these nodes of our network can be all sorts of different devices. We can start from simple photonic devices that can perform cryptographic applications, and this is and that can measure and detect and that can send and measure simply, let's put it, quantum states, and then we can increase in complexity by adding quantum sensors, by connecting quantum processors, quantum memories, etc. And this, of course, these are linked. Photonic resources are particularly important for linking these devices. And so the communication is happening through optical fiber or free space links that can include satellite communications as well. Next slide, please. So here I have attempted, based on this description, to look at an evolution and how this evolution in technology and application will look like in the next few years, where we see that we're going through several stages, in particular 3 major stages of such networks, where we see in the first stage what we know how to do today, where we have gone beyond proof of principle experiments, in particular for quantum key distribution and quantum random number generation, which are basic functionalities, but also, as you see on the upper part of the slide on the left, in the dark blue color, you see that there is also a bunch of other applications and protocols that belong to this category, this stage of quantum networks, where essentially, because these are point-to-point links and we know how to transfer information in this sort of prepare and measure way, then we are, if we want to get over the loss limitation of these physical links that are based on quantum resources, we need to use trusted repeaters where the information goes into the classical domain for if we want to extend the distance. In the second stage of these networks, we will add entanglement, and then the entanglement distribution, and then of course this gives rise to more advanced functionalities. We're talking here about opening the way, for example, to much stronger security guarantees through device independence. We're talking about further also communication protocols that are based on multipartite entanglement, like secret sharing or anonymous communication. And then in the third and the more advanced stage of quantum networks, we will also add advanced devices like quantum memories and repeaters, and finally quantum processors, and then this will open the way to even further and more increased complexity functionalities that go beyond the field of cryptography and security and touch upon computing. So we will be having access here and computer and distributed sensing, so we can do clock synchronization, blind quantum computing, distributed computing, and of course this needs this interconnection of quantum processors via memories and repeaters to be able to perform this type of applications. So let me show you now, next slide please, some limitations that we have, for example, on the current status in this first stage of the quantum networks that I showed to you. So here you see a review of of quantum key distribution in particular systems, these point-to-point systems as they look today in practice. So this graph was done with a few colleagues a few years ago, but it's still so of course some stuff have changed since. So you can see, for example, that protocols like the measurement device independent protocol has gone up to the level of being a mature protocol. We also have new protocols that have showed up, like twin field cryptography. And so there are some moving in this in the several types of protocols. This is a very rich and ever-evolving field. So for this functionality, there is a lot of innovation happening at all levels. But what is important to point is that there are fundamental limits in the rate and in the range. And there are also other challenges associated with certain systems, in particular technological challenges of how to improve the performance, how to make the security more robust, and how also to integrate better into networks, how to develop good quantum random number generators, and then advance the test relevant use cases in this application layer that we saw earlier, and also advance towards the third stage quantum network technologies that I was showing to you. So in the next few slides, I'm going to show you how presently the European quantum technology flagship projects are attempting to address these challenges, and what are the ongoing efforts within this roadmap in Europe. So I'm starting, next slide please, with the Q-range project. So this is a project that is one of the 4 quantum communication pillar quantum technology flagship projects. So it targets quantum number generators, and in particular cheaper, faster, and more secure. So there is 3 targets in 4 QRNG systems in this project, and you see here that there has been progress in all 3 directions with very compact, increased security, for example, in particular by looking in semi-device independence and protocols based on self-testing for quantum random numeration, and also very fast devices. In the next project, this is the Unicorn project. So the consortium covers a number of countries around Europe. Next slide, please. So the major subject of Unicorn is this quantum communication in chip. You see here a selection of modules that have been developed, the technologies that have been developed inside this project. So you see, for example, QKD transmitter based on indium phosphide technology, QKD receiver that is extremely low noise for continuous variable QKD based on different types of technologies as well. And also going towards the second stage of the quantum networks, you see quantum sources and tangle photon sources based on time bin encoding, and also polarization encoding, also integrated using novel polymer-based integration platforms. So this is a good opportunity to tell you that photonic integration is one of the major challenges in the field, not only for quantum communication, but for the entire field of photonic-based quantum technologies. So please note that there is a dedicated workshop for this on Wednesday morning in the EQTC conference if you are interested in this topic. So a use case based on this model, a use case that the Unicorn project is considering, next slide please, and it very much fits into this application layer that I was showing to you for intermediate stages of the quantum networks, is based on one-time programs for cloud-based processing, and so this is an advanced quantum cryptography application that can be enabled by the type of devices that we just saw, and that advances the technologies towards this second stage of quantum communication networks, where we are able to address more advanced functionalities. Finally, the third quantum flux project, next slide, is CIVIC. So this is a project that is led by ICFO in Barcelona, and in a nutshell, what CIVIC wants to do is to advance towards telecom integrated and network integrated and cost-effective QKD devices based on continuous variable encoding. So we see in the next slide some main results and highlights from this project that include the development of software-defined network technology, but also continuous variable QKD devices based on different photonic integration platforms. Again, you see photonic integration that comes into the picture. Also, the integration of popular techniques in coherent classical optical telecommunications like digital signal processing and machine learning for optimization. And you see also a boost in security proofs to be able to adapt security analysis to the current requirements of these advanced QKD systems. And finally, you see an effort towards protocols beyond key distribution, in particular for quantum money or multi-user networks, and in particular based on measurement device independent paradigm. And you see that the devices going and network components that go into the direction also push the technology towards more advanced functionalities. So these three projects that I have summarized, whose results I have summarized briefly here, essentially belong to, except for a few exceptions like the ones that I talked to you about, entanglement-based systems, that belong to this category of protocols where we have, as I was explaining to you earlier, we have to trust the intermediate nodes of the communication network, exactly because if you want to extend the distance, you need to go through intermediate nodes, but this exceeds the available distance, the range of your systems, and therefore you need to be able to reveal the quantum information, like the key, for example, in the intermediate node, and then push it forward through these nodes. Now, for the next stages of the quantum networks, next slide, please. You see that there is, for instance, the work that is happening in the context of the Quantum Internet Alliance, the fourth quantum communication pillar project, where the idea is to not need any more distrust scenarios and be based on go for end-to-end security and advanced applications towards the third stage of the quantum networks that I was showing to you. And for this, we need to advance technologies towards quantum memories, quantum storage devices, and quantum repeaters and processing nodes. So I'm showing to you here a couple of highlights from European teams in this direction. We see, for example, the entanglement distribution, entanglement swapping between three nodes using NV centers that was achieved in Delft recently over a few meters. We also see the experiment at ICFO in Barcelona that entangled quantum memories based on solid-state qubits, and also the record high quantum efficiency of quantum storage efficiency of quantum atomic cloud quantum memories here in Paris that were also achieved in the past few months. So you see there is big progress, impressive programs happening in this direction, and these are the results that I have selected from Europe, but there are also equivalent nice experiments abroad as well in other areas of the world. There are, of course, still important remaining challenges, in particular with respect to the trade-off between efficiency and storage. Storage time, this is the major challenge for quantum memories. And of course, the entanglement generation rates and the range remain limited in this type of systems. And so it's particularly important to keep on trying to demonstrate a quantum advantage, as we said earlier, for intermediate stage quantum network applications. To do this, an important tool, and we'll see this in the next slide, is testbed development. So there is a big effort going worldwide towards the practical deployment of quantum communication devices. There is many reasons to do that, as we're going to see. This allows us to test interoperability, to benchmark use cases, to standardize interfaces, and also to test, of course, more and more advanced devices into real conditions. So you see that this is what the biggest quantum communication testbed in the world is currently in China. That includes a 2,000-kilometer backbone network, and all types, as you see, different topologies, which are all based on this trusted repeater network that I showed to you earlier. The equivalent, the corresponding effort in Europe is embodied by the OpenQKD consortium, a very large-scale project that includes all types of different stakeholders in the field. And you see, next slide, please, that there is a clear interaction between the research and development efforts that are happening in the projects that I described to you before, that provide technological capabilities to the OpenQKD network, which also reciprocally it gives deployment possibilities. And this, you will see, that it covers a very wide range of use cases that cover the major sectors of social and economic activities currently, going from healthcare to government communication to finance, mobility and navigation, and of course energy sector, and of course activities that are linked to digital infrastructure like storage, cybersecurity, cloud computing, and high performance computing. All these use cases are covered by this deployment possibilities, and this of course needs this type of experimental platforms to demonstrate that it's possible to actually do it in practice. And the major goal of such initiatives is to push for a European QKD industry and also lead to a pan-European quantum network. Of course, the description would not be complete if we didn't add into this the space efforts. Next slide, please. So it's important to understand and to complete here the picture that terrestrial and space-based networks work hand in hand together. They are not only are they important for an integrated infrastructure, but they also are fallback options, one for the other. Space quantum networks offer even more use cases because they give access to, they bring quantum applications, they give global reach to all quantum applications, of course, given the technology becomes available, and they also offer access to inaccessible to locations that for some reasons cannot be reached with fiber infrastructures, for many reasons, either because they are isolated or inaccessible, or for some reason we cannot access them. So obviously you see here in the roadmap that we have prepared in the European Quantum Space Network that space quantum networks follow the same steps as the terrestrial ones, and there is major efforts underway now to push the technology so that it becomes space certified and it becomes available to be able to push these quantum technologies also in the space domain. So all of this together, next slide please, leads us to this major initiative for the next 10 years in Europe. That is a joint effort between the European Commission and the European Space Agency, and that the European Quantum Communication Infrastructure that wants to bring together these terrestrial and space segments and interconnect national quantum communication infrastructures to unleash the full potential of quantum technologies. So let me conclude in the next slide with a few important take-home messages and key challenges that need to be considered on the road to deployment of quantum communication technologies. So I hope I have shown to you that such integrated ground and space infrastructures will be essential in the future quantum safe world, that they can cover a number of applications, so that we have seen that actually the application set for quantum networks is rich, increasingly advanced, and we don't even know really all the applications in the same way that we didn't know all the applications of the classical internet. We actually do not currently know all the applications that the quantum internet will bring to us, but already we have a good baseline to work with for building the fundamental blocks and showing a quantum advantage for many interesting functionalities. It is important also to understand that these successive stages of the quantum networks that I showed to you will rely on the progress on a supply chain that will be useful for each one of the stages, but also for going beyond quantum communications to the other field of quantum technologies. And also that quantum communication technologies, in the same way that quantum computing will integrate into current high performance computing efforts, in the same way quantum communication cannot be conceived independently. It has to be conceived integrated into the classical communication and classical cryptographic practices that are available today. And only by doing hybrid solutions, it will be possible to advance in ways that can be acceptable for the end users. So this brings me to, and this I will conclude, to the key challenges that I believe there is an urgency in cybersecurity today, that with major points that include how to protect the resilience of the communication, how to prioritize the actions that are necessary for protecting strategic assets, and also how to move towards hybrid solutions. And also there is a major work towards defense in depth, where quantum communications can play a major role. We also see that there is a big effort toward standardization and, of course, and certification, and we need to work with cryptography and network security and network experts to create compelling use cases for market adoption. We need to protect the digital sovereignty of Europe, and of course to make sure that we integrate efficiently developments and new frontiers in research and technology that are happening every day. There is already now a huge number of new protocols and new devices that we need to integrate into this picture. And with this, I conclude. Thank you very much for your attention.
Thank you very much, Eleni. So we don't have a lot of time for questions, but we got one from Angela Chiatto, and she's asking about how machine learning could improve QKD systems.
So there has been work already into some machine learning optimization techniques. So this is not quantum machine learning, I should say. So these are machine learning optimization techniques that have been used to, for example, to accelerate error correction and parameter estimation that are necessary post-processing steps in quantum key distribution systems. So of course, if I can provide more information for this, please don't hesitate to ask me for reference. But I think there is even more going to accelerate this trend of including this type of optimization techniques for making even high performance systems, essentially.
I believe there are no more questions, but I have one quick question for you. So, because you didn't tell us much about your research, let's say, no, it was more an overview about the. So, what would be the challenge you would like to solve?
So I'm particularly very much interested into this intermediate stage I talked about. So for me, a very big challenge is to use technology inspired from quantum key distribution, in particular these very advanced devices that we have, and adapt this to intermediate stage quantum communication protocols based usually on entanglement, where we can show, for example, what I'm really interested in and working now in the lab is to demonstrate the proof of principle experiments for anonymous communication, electronic voting. and communication complexity as well, that I didn't have the time to touch upon at all, which has the goal of improving resource efficiency in quantum networks. So I'm interested in developing technologies and it's also the interface between computer science and physics, because you need to properly benchmark the quantum advantage for all of these protocols. And I want to show that even while we're going through the efforts for quantum repeaters and technology and memories and of course processors, we can actually solve for useful tasks a quantum advantage today with a communication network. So for me, this is a major challenge right now. I think Eugene has a question or a comment.
Yeah, well, may I abuse my position as a speaker. So a very egoistic question, so to say. In my talk, I presented this wonderful entangled source of light with high purity and large entanglement between the colors. One of them at the moment is 106, but it can be 1.5 microns. And the other one is targeted towards the atomic memory. Mm-hmm. So what's the best place to sell such a thing for quantum?
That sounds like an extremely useful resource for quantum networks, honestly, Eugene. So we should talk.
Okay, good, thanks.
Good.
Okay, there was one more question, but I'm sorry, I cannot take it now because we should stick to the time. We thank Eleni again, and we move to the next speaker. Thank you very much, Eleni.
Thank you.
And yes, our third and final speaker will be Stacy J. Free from QSoft in the Netherlands. So, yes, and CWI, sorry, I forgot. Yes, so please go ahead.
All right, thanks for the introduction, and thanks everyone for being here for my talk today. I'm going to be talking about some of the recent advances in quantum computing from the last couple of years, and in particular, I'm going to talk about advances in quantum algorithms, which is what my research is about. And I don't know if you've noticed this as well. I definitely noticed when I was preparing my talk that many results in quantum algorithms are not straightforward, even just to state them. You know, you would think that it would be easy to just say, well, we solved this problem, and this is why the problem is important, and this is how fast the quantum algorithm is, and you know, it's this much faster than the best classical algorithm. But unfortunately, the field is actually not at the point of maturity where we have many results of that form. Most of the results in quantum algorithms are much more nuanced. Like we say we can solve this problem, and it's related to an important problem in this somewhat roundabout way. But then there are these caveats, and also we don't know if maybe a classical computer could be just as fast. This kind of thing doesn't really make for a very compelling talk. And I know that what people really want in this kind of like a broad talk is that, you know, you want simple answers to simple questions. And so I decided that instead of giving like a really complicated talk, I'm just going to give some simple answers to what I think are probably the most basic and simple questions about quantum algorithms that are on everyone's mind. The first one is, how many quantum algorithms are there? And, you know, like, has this number changed over the last couple of years? Have we maybe found some more quantum algorithms? So I'm going to attempt to give an answer to this question. But you could have all the quantum algorithms in the world, and that won't help much if they're just not very good quantum algorithms. So the second basic question that I want to answer in my talk is, what is the best quantum algorithm? So I hope that I can answer these simple questions and you can come away from my talk feeling like you know a little bit more about the state of quantum algorithms. So to answer the first question of how many quantum algorithms there are, I want to talk about a nice movement in the field of quantum algorithms in the last couple of years that has recently been dubbed a grand unification of quantum algorithms. So to start off, I'd like everyone to try to think of 3 quantum algorithms. So what comes to your mind when I ask you to think of 3 quantum algorithms? Maybe one algorithm would be Hamiltonian simulation. That's the original application of quantum computers, which, as we all know, were first conceived of by physicists who noticed that to simulate quantum mechanical systems, it might be necessary to employ a computer that was natively quantum, which we now call a quantum computer. And you also probably thought of Shor's quantum algorithm for factoring an integer. This was the first dramatic quantum speedup for a natural problem outside of quantum physics, the problem of factoring an integer into primes. And this problem had been studied for a long time before quantum computers and resisted significant efforts to come up with an efficient classical algorithm. So Shor's efficient quantum algorithm was significant because it showed us that quantum computers would have broad implications. They wouldn't just be some kind of niche thing in physics. And then what's the third quantum algorithm you probably thought of? I'm willing to bet that many of you thought of Grover's algorithm for quantum search, which is the other big quantum algorithm to come out of the 90s. Now, this algorithm only gets a quadratic speedup, but it applies in so many places that its projected impact in the long run is easily as competitive with Shor's algorithm. And I'm guessing when I asked you to think of 3 quantum algorithms, the majority of you thought of exactly these 3. And people used to actually joke that there are only 2 quantum algorithms, and they meant Shor's algorithm and Grover's algorithm. They were not counting Hamiltonian simulation, I think, because the problem it solves is so native to quantum computing. But it's of course not true that there are only 2 or 3 quantum algorithms. There are many more quantum algorithms, but as far as I know, it is true that they can all be seen to have somehow sprung from one of these 3. So there are algorithms where we encode a problem into a Hamiltonian in some way. This is true, for example, of the HHL algorithm for solving quantum linear systems. And this also captures things like continuous time quantum walks or adiabatic algorithms. There are algorithms where the major quantum workhorse is the quantum Fourier transform. This includes Shor's algorithm and very closely related algorithms for other number theoretic problems like discrete log, and also things like the Bernstein-Vazirani algorithm. And then there are algorithms that somehow generalize Grover's search algorithm, like amplitude amplification, which is the main subroutine in numerous quantum algorithms, and then discrete time quantum walk search algorithms also fall into this category. So if we take the sort of simplified view that there are only 3 quantum algorithms, then the best way to make progress would be to increase the number of quantum algorithms to 4. And what that would mean would be that you would come up with a new quantum algorithm using an entirely novel idea that did not fit nicely into any of these 3 categories. As far as I know, that has not happened yet, but something else that's quite conceptually interesting happened in the last couple of years, which is that instead of increasing to 4, the number of quantum algorithms decreased to 1, which might seem like a step backwards, but what has actually happened is that we've unified these 3 techniques into a single well-understood framework called the quantum singular value transform algorithm. This means our conceptual understanding of what all quantum algorithms look like has greatly improved. We now have one algorithm that we can sort of tweak the parameters to get any of these things, and then we can kind of try and compare like what exactly is the source of the quantum speedup. So what is this quantum singular value transform algorithm that I claim captures all known quantum algorithms? Well, just very briefly, the idea of the quantum singular value transform algorithm is that if you have a unitary with some matrix A embedded in it, then by interleaving this unitary U with some rotations, you can implement a unitary with some polynomial of A embedded in it. And when we say we apply a polynomial to A, what we mean is that we apply the polynomial to the singular values of A, hence the name. There are various ways of implementing a unitary with a matrix A of interest embedded like this, and it's not difficult to see that if, with the right polynomial, you could approximate things like the inverse of A or the exponentiation of A to get Hamiltonian simulation. But it turns out that this framework goes beyond even these types of algorithms in its generality. And for a very nice overview, I recommend the PhD thesis of Anders Gillian, who's a former CWI student who kind of spearheaded this whole effort, or there's a recent survey, a very nice survey by Martin et al. So this framework captures virtually all quantum algorithms we know of, and it has helped to clarify several results in quantum algorithms as well as come up with new ones. Before I move on to the second part of my talk, I want to briefly mention a particular area that has been greatly clarified by this framework. And that's a certain area of quantum machine learning that has been hit by a recent epidemic of dequantization. So let me explain briefly what I mean. Quantum mechanics is described by linear algebra. And so linear algebra is a natural place to look for problems that a quantum computer might be useful for. After all, simulating a Hamiltonian is in some ways a linear algebraic task. And indeed, using ideas from Hamiltonian simulation, more than a decade ago, Harrow, Hasidim, and Lloyd gave a quantum algorithm for solving a linear system, famously with some caveats. So recall that the problem of solving a linear system is to find a vector x that is a solution to A, x equals B, where A is a matrix and B is a vector. But the quantum HHL algorithm mentioned here does not solve this problem exactly. Instead of finding a solution x, it lets you produce a quantum state whose amplitudes encode the solution x, the linear system. And only if the linear system is sparse, and if you somehow have a way of encoding the vector B into a quantum state efficiently. So there are real caveats, but on the other hand, if you do have a sparse A and a vector B that you can efficiently encode into a quantum state, and you can somehow make use of having this quantum state X rather than an explicit description of the solution X, well, in that case, the quantum algorithm of HHL depends only logarithmically on the dimensions of A and B, whereas it's difficult to imagine a classical algorithm not scaling linearly in these dimensions. So this could potentially give an exponential speedup for some linear algebra problems. So this algorithm, and actually all the algorithms I'll mention on this slide, can be seen very nicely in the quantum singular value framework, although these algorithms, or at least most of them, predated. But one nice thing is that the quantum singular value transform framework gives a nice unified picture of what seemed like previously different techniques. Anyway, one reason the quantum linear algebra algorithms like the HHL algorithm are so exciting, the caveats aside, is that lots of data processing and machine learning tasks are also based on linear algebra. And this is one of the reasons why there has been some hope that quantum computers could be used to get even exponential speedups in machine learning. And indeed, with again, the same caveats I just mentioned, the HHL algorithm could be applied to data fitting via linear regression, giving slightly more concrete hope of an exponential speedup in machine learning algorithms. And I'm going to borrow the design of these slides from Ewan Tang, who uses this nice color coding to illustrate how good of a candidate something is for an exponential quantum speedup for a machine learning problem. So this data fitting algorithm is for a more concrete problem in machine learning, so it brings us closer to the stream. But of course, it has these caveats of needing sparse data that can be encoded in a quantum state and then needing to make use of the output state somehow. But it's definitely something that deserves attention, since if these things could be overcome, there would be huge impact here. And so progress continued with more new and exciting results, still with some caveats, but some things we're getting more and more hope that we might get an exponential speedup in machine learning. You can see things kind of heating up on the slide. And in fact, this result in orange, this recommendation system of Karanitis and Prakash was particularly exciting because it actually managed to get around the caveats I mentioned in some way or another. It didn't require the data to be sparse. It came up with a reasonable setting where the input could be loaded efficiently into a quantum state, and it even managed to concretely make use of the output, even though it was encoded in a quantum state. And this paper actually solved basically end-to-end a concrete problem that had come up in classical machine learning, which is using existing knowledge of people's product preferences to recommend a new product. So this was a really exciting result. But then in 2018, an undergraduate student named Ewan Tang came along and laid waste to this whole landscape of hope for exponential speedups in this way. So now you can see things by already 2019 had cooled down quite significantly. And what happened here was, well, all these works considered linear algebra problems in a specific setting that made them amenable to quantum algorithms. And this setting had not been specifically considered in classical algorithms, but what Tang found was that this specific setting was also pretty amenable to classical algorithms. And she showed that these kinds of problems could be solved with classical computers only polynomially slower than the quantum algorithms. So it's not that anything was found wrong with these quantum algorithms, but rather that their usefulness was diminished by the fact that there were new classical algorithms that could solve the same problems in the same settings with only a polynomial slowdown. In some sense, you could see this as a very successful effort in making all of these algorithms very near term. But for those of us who are interested in the usefulness of quantum computers, this is maybe considered a little bit too successful. And here the quantum singular value transformation framework played a huge role, because on the one hand, it helped formalize and improve many of the kinds of quantum algorithms shown here, But on the other hand, the clean understanding also helped to see where efficient classical algorithms could also be used to dequantize some of these quantum algorithms. And so what about these algorithms that have not been dequantized to get classical algorithms? Well, here the quantum singular value framework sheds some light on why some quantum algorithms really do seem to be getting a exponential quantum speedup, and that's in the setting of sparse data. This seems to be a setting where we might be able to get very efficient quantum algorithms even where no efficient classical algorithms exist. But this kind of data, well, the kind of data we might want to process and practice in machine learning has no particular reason to be sparse. So I think, it's fair to say that this was a huge blow to the effort to come up with exponential speedups in quantum machine learning. And well, there's still a lot of work left to do if we want to find a dramatic speedup from quantum linear algebra. And it's also unclear for which problems. Okay, so we've answered the first question. There's one quantum algorithm. And that maybe actually seems to make my second question somewhat trivial. But the perceptive viewer may have noticed that I actually mentioned a whole bunch of quantum algorithms. And what I hope I've actually conveyed in the first part of my talk is that our understanding of the overall landscape of quantum algorithms has improved by having a new paradigm for understanding existing quantum algorithms and also designing new ones. And this has helped us on the one hand see why certain problems are amenable to quantum solutions, but it has also helped us to see areas where there are also good classical algorithms. And somehow at the end of the day, what we really want to understand is when we can efficiently solve a problem with a quantum computer, but not with a classical computer. And this brings us to our next important question. What is the best quantum algorithm? What makes a quantum algorithm good? Obviously, it should be fast, but as we've seen, it should also solve a problem that classical computers are bad at solving. So what we're really interested in is what is the best separation we can get between quantum and classical algorithms. And that's what I want to talk about in the second part of my talk. When you come up with a good quantum algorithm for some problem, there's always a chance that there's an even better classical algorithm unless you can prove a classical lower bound. And in practice, these sort of really proven separations in the power of quantum and classical computers require us to work in the model of query complexity. And in the last couple of years, the question of what is the biggest separation possible between classical and quantum query complexity has gotten a lot of progress. And so I'm going to spend most of the rest of my talk setting up the details of this question, and then I will tell you the answer. So I want to introduce and motivate query complexity. If you know what query complexity is, and you also know the answer to the question, why are theorists always going on about query complexity, then you might be bored for the next couple of slides. I apologize. But for everyone else, suppose you want to solve some problem f. So you want to compute some function f on some input x, which it could be, for example, that x represents an integer and f of x is the smallest non-trivial factor, or x could represent a network and f of x is 1 if and only if there's a path between two special nodes s and t of length below a certain threshold c. There are many possible problems you might want to solve, and the million-euro question is always, how many operations are needed as a function of n, the length of the input, to compute f of x? And specifically, what we here usually care about is how many operations are needed for a quantum computer versus for a classical computer. And we're very excited, of course, when the classical number is much higher than the quantum number. However, questions like this are very difficult to answer. One direction is sort of easy. If you come up with an algorithm, this gives you an upper bound on this number. If it's a classical algorithm, it's an upper bound on the number of classical operations. If it's a quantum algorithm, it's an upper bound on the number of quantum operations. But you only get an upper bound because you don't know if your algorithm is the best possible. So coming up with an upper bound boils down to coming up with an algorithm and counting its operations, which is tedious but often possible. On the other hand, lower bounds are much more difficult because to prove a lower bound, you have to prove a statement about all possible algorithms, that they can't be better than a certain complexity. And we've had much less success in proving lower bounds on the number of operations needed by classical or by quantum algorithms than we've had with upper bounds. But if we're interested in separations between quantum and classical, we need quantum upper bounds and classical lower bounds. So let's see an example of how we can prove a really simple classical lower bound for a very simple function. The function is the OR of n bits. So f of x is 1 if and only if at least one of the bits of x is 1. And if x is just all zeros, then f of x is 0. And this is the problem solved by Grover's algorithm. I claim that if you want to solve this problem with success probability, say 2/3, then you'll have to do at least like 2/3 times n operations. And the way we can see this is by considering any classical algorithm and looking at which bits of the input it reads. So the input is going to be stored in memory somewhere, and in order to learn about the input, your algorithm will have to do some read operations. And if it only does, if it does less than 2/3 n operations, then it certainly does less than 2/3 n read operations. And so, for example, there must be some bit of the input that is read with low probability, like probability less than 2/3. And if all the bits are 0, aside from some unread bit, then it will not be possible to decide if the output should be 0 or 1. A read to an input bit is called a query, and often the easiest way to lower bound the total number of operations an algorithm needs is to lower bound the number of queries it needs, like we did here. The number of queries an algorithm uses is called its query complexity, and a nice way of understanding the question of the number of operations is to just look at the number of queries. This gives rise to the notions of classical query complexity and quantum query complexity. So what exactly is a quantum query? Well, a classical query is an operation that for any I returns the ith bit of the input. We usually model the algorithm's interaction with the input by just supposing it implements this operation. And similarly, a quantum query is a unitary that implements some unitary version of the same operation. But of course, in the quantum case, we can query a superposition of different I's, which turns out to be quite powerful. So query complexity is a simple way to measure the complexity of algorithms. And the fact that it's simple and it's particularly, it's possible to give lower bounds here isn't the only reason we study query complexity. It also allows us to look at some kind of general problems called black box problems, and I'll get to that in a second. But for a problem F that we might want to solve, R of F will denote its classical randomized query complexity, the number of queries needed by a classical computer, and Q of F will denote its quantum query complexity, the number of queries needed by a quantum computer. Okay, so this is query complexity and why we care about it. And now I want to talk about what is the biggest possible separation we could have between R of F and Q of F for any function F. And the question of what is this largest possible separation was formally posed 20 years ago. And through some exciting recent work, we've pretty much settled this question. At the time when the question was asked, the best separation known was log n quantum queries versus n to the 1/2 classical queries, for example, from Simon's algorithm, or there were a couple of algorithms known with this separation. Now, before I talk about better separations that came later, I want to address the question of what would be the best possible separation we could achieve. And I claim that it's 1 versus n. We need at least one quantum query, because if you don't query the input at all, then your answer is independent of it, and then the only functions you can compute are constant functions. But for these, classical computers also need 0 queries, so there's no separation. And then the highest possible classical query complexity would be n, and that's because you can always have a classical algorithm that just queries all input into its algorithmic workspace using n queries, and then just uses non-query operations for the rest of the algorithm to compute f of x. So the best separation we could possibly hope for is 1 versus n. Now you might be thinking, where are the polynomial versus exponential speedups here? Where are the problems where a classical computer requires exponential time, but a quantum computer requires polynomial time? And these are not fully captured by the query model, but it does give us some insight into them. So I'll try to explain that with a brief digression. In the quantum query model, we assume the algorithm has some way to implement the unitary ux, which given I computes the ith bit of x. And we use this to compute some property of x, like asking if x has any 1s or if it's just all 0s, which is what Grover's algorithm computes. So far, we've been assuming that the way this is implemented is that we have an n-bit string x stored in memory, meaning our input size is n. But the algorithm works no matter how you implement ux. So let's for a moment rename the string x as f, which can be equivalently viewed as a function with domain 1 to n and range 0, 1. We could get this function as input by being given the function as a long string or table of values stored in memory, but it also might be that we get a shorter input that allows us to compute this function in a different way. For example, the function f could be some special kind of function specified by a shorter string z that we have in memory as input, and then we have some subroutine that computes f sub z of I for any z stored in memory. Concretely, maybe z is specifying a network, and we might interpret I as a path of the network, and fz is a subroutine that checks if this path has length below a certain threshold. And then if we run Grover's algorithm, implementing the query operator in this way, it will tell us if there exists a path with, with length less than this threshold. And if the actual input size is polylogarithmic in n, then a quantum or classical algorithm with complexity big N is actually exponential in little n, the input size. A major caveat is that any lower bound only applies if we assume there is no special structure of f sub z that we can exploit, and all we can do is treat it like a black box. And in some cases, this is definitely not true. So while the query model can give us some evidence where we might get exponential speedups, it can't actually prove a true exponential classical lower bound. Okay, but returning to the question of what is the largest possible separation between quantum and classical query complexities, in 2009, Aronson introduced a problem called correlation that could be solved with a single quantum query and showed a classical lower bound of n to the 1/4 queries. And Aronson and Ambinas later improved this classical lower bound to n to the 1/2. So let me quickly describe the problem of correlation. For correlation, it's convenient to view the input as two strings of length n/2, each of which we can query. Now, if we consider a quantum circuit that looks like this, it's just Hadamard gates, query the first string, Hadamard gates, query the second string, Hadamard gates. And then we define phi of x to be the probability that if we measure the output of the circuit, we get the all zero string. Then phi of x is actually just a measure of the correlation between x1 and the Fourier transform of the string x2, hence the name correlation. The correlation problem is to give a 1-bit estimate of this quantity, specifically decide if it's at least 2/3 or if it's at most 1/3 when promised that one of these is true. So it's easy to see why we can solve this using two quantum queries, and in fact, it's even possible to reduce to a single quantum query. But the really hard part is showing that a classical algorithm would require many more queries than that. And Aronson and Ambinas also gave a k-fold version of correlation called k-correlation, which is the same thing except we split the input into k parts, as in this circuit here. And they conjectured, but did not prove that this optimally separates classical and quantum query complexity. So they conjectured a randomized lower bound, but did not prove it. Okay, in the last couple of years, there's been a series of work towards proving this conjecture. In 2019, Tal showed that a new problem related to k-correlation called k-row relation gave a separation of k/2 versus n to the 2/3 minus 1/k. This is true for any constant k. And last year in two simultaneous results, the separation was improved by showing a classical lower bound of n to the 1 minus 1/k on k-correlation. And what that means is that for any constant epsilon, as small as you like, there's a problem with constant quantum query complexity and classical query complexity n to the 1 minus epsilon. That's almost as good as the 1 versus n, or at least constant versus n separation that would be the best we could hope for. But it's a little bit worse, so you might wonder if we could do even better. And it turns out that the separation is optimal, which had been claimed in previous work, but a bug was found and a correct proof was given just this year. So now the question of the optimal pre-complexity separation is really settled. It's not possible to get 1 versus n separation, but it's possible to get extremely close to this. Okay, so I think I should wrap up because I'm a bit over time. So I was not being entirely sincere when I said my talk would give simple answers to these questions. Of course, the ultimate goal in quantum algorithms is to get to more simple answers, more algorithms where we can say, this algorithm solves this problem in this time, which is a significant speed up over the best classical algorithm. But right now, there are some barriers to getting these kinds of results. But in the last few years, we've made some real progress on the theoretical framework that would be required to get results like this. Thank you very much for your attention.
Okay, thank you very much for your talk. Very nice. So we got many questions. I mean, there is no time to read all of them. I'm going to leave them there. I don't know if then later you will have the possibility of reading them. So maybe I will take the first that was asked. So it's by Adam Miles Lewis. And he's asking if you agree that quantum computers will be more tools for big combinatorics than for big data.
Well, I mean, yeah, that's maybe a good question. I think maybe my first answer would be we really don't know. So that there's a I think maybe a good takeaway from my talk is that we really don't know what quantum computers will be used for. There's a lot of research left to do in this area. yeah, so I think maybe yeah, I mean, we can get quadratic speedups in some machine learning problems, and similarly, we can get up to quadratic speedups in certain combinatorial problems. I think it's not yet clear which of these will be more useful in practice.
Okay, so I believe we should. I mean, we have 1 minute left, so I'm sorry, we should stop here. I just want to thank the 3 speakers for the very nice talks, and well, enjoy the conference. Bye.